Hi guys, and welcome to project 3 of the data series. In this episode, I plan to cluster mixed data from a heart failure clinical record dataset. And by mixed data, I mean data that is both numerical and categorical. So for the first step here, we're importing and exploring our data. So here I've imported warnings to ignore all warnings that come up, also pandas to import our data, and I've also imported NumPy. So in this line here, I'm ignoring any warnings. Here I'm reading the data and storing it under the variable df. You should find in the description a link to the code and also data. So here I'm printing the size of our data frame, and we're also going to display the first few rows using the head method here. So if you run this here, so here we can see the data that we're working with, such as age and anemia, diabetes, platelets, and so on and so forth. We can also check the data types of our data frame by using the dtypes method. And if we run this here, we can see that all of our variables are either integer or float. So in this project here, I just plan on focusing on clustering 5 variables, that is age, sex, serum sodium, platelets, and smoking. So here I've defined these columns in which I'd like to cluster, and then I just change the data frame to just include those columns. We can run this here, and there we go. So before clustering our data, it's important that we scale it to ensure that each feature is roughly on the same scale, so the clustering isn't biased towards a particular feature. So here we import the standard scalar function from scikit-learn. We also define our numerical features and our categorical features. And here we're defining our scalar as the standard scalar. So we're just going to create a copy of our data frame and store it under df_scale. And we're just going to be scaling our numerical features, which is done here. So we can run this here. And that's done. And let's now just have a look at our new standard scaled data frame. So we can run this here and we can see it. We can see that our age, serum sodium, and platelets have been scaled. So here I'm going to remove any outliers that exist outside 3 standard deviations of that feature's mean. And I've realized here that I've actually missed another feature. So here I'm basically just including those that are within 3 standard deviations, i.e. removing those that are outside 3 standard deviations. And we're doing this for age, for platelets, and also we need to do this for serum sodium. And then we can run this here. So we see here now that our data frame takes the shape of 293 rows and 5 columns. Whereas before we had 299 rows, so we have removed 6 rows. So before we go on and apply our clustering algorithm, it's important to get an idea of how many clusters should we be putting our data into. And for that, we're going to focus on 2 methods here, the elbow method and the average silhouette method. So before applying these methods, we actually have to do a little bit of a setup for our K-prototypes clustering algorithm. So if you guys haven't heard of K-prototypes before, there should be a link in the description where you can read more about this algorithm. I also go into a little bit more detail in my Medium articles, which should hopefully also be in the description. But essentially, the way that K-prototypes works is by using the standard Euclidean distance for measuring the distance between numerical data points, and then uses the simple matching dissimilarity measure for categorical variables. And now that we have these 2 distance metrics defined, one for numerical features and one for categorical features, we can then apply k-means clustering on these newly formed distances. So in order to apply K-prototypes algorithm, we actually have to feed in the indexes of our categorical features. So here I'm just looping through our categorical columns. In this case, it's just sex and smoking. And then I'm just appending the index of these categorical columns into our list here. And if we run this, we can see that our categorical columns are in position 1 and 4. We can check that. So we have sex in column 1 and smoking in column 4. So now we can apply these two cluster evaluation methods. So with the elbow method, we look at the total within cluster variance for different numbers of clusters. So here we see the different costs, which is the within cluster variance for different numbers of clusters. And then we just choose the number of clusters, where essentially adding any more clusters doesn't really have a huge effect on the cost. And that's found usually at roughly the elbow of the curve. And here I would say this is roughly at 5 clusters. We can also look at our average silhouette method. I won't go into too much detail, but essentially it takes a value between -1 and 1. 1 indicating that our data points are very well clustered, and -1 indicating that our data points are poorly clustered. And we can run this method here. And here we see our average silhouette scores for different numbers of clusters. And we see here that 5 clusters results in the maximum average silhouette score for clusters between 2 and 10. So from these two methods, we would say that 5 clusters seem reasonable, but we actually have quite a low average silhouette score at around 0.21, suggesting that the clusters actually aren't that distinct. So here we can now apply the K-prototypes clustering algorithm for 5 clusters. We set the initialization method to Huang, and if you guys want, you can read more about this initialization method in the description. We set the number of iterations equal to 25, and that's how many times we are initializing our centroids. And we set the random state equal to 42. We then apply this algorithm to our scaled data frame, and we also feed in our categorical indexes. So once that's been applied onto our data, we can then get the cluster labels, and we can add these cluster labels to our data frame. And lastly, we can check if the clusters have been added by just printing the first few rows of our data frame. So if we run this cell here, we can see our data frame. We can also see this new cluster column, and we can see here that the patient in row 0 is put into cluster 0, the patient in row 1 is put into cluster 3. And this hopefully should be for all of our patients. So now that we have clustered our data, we can go on to do some exploration. And the first thing that I did here is what's called principal component analysis. I won't go into too much detail of this algorithm. I do plan to go over algorithms like PCA and UMAP in hopefully future episodes. But essentially, PCA is a dimension reduction algorithm that tries to maintain some of the structure in higher dimensional space and reduce that into lower dimensions. And here I'm applying the PCA algorithm to our scaled data, reducing it from 5 dimensions to 3. And the reason why I'm applying PCA is so that we can get a visualization of our data. So here I'm making a 3D plot of our principal components. And for that, I'm using the Plotly library. So we can run this here and have a look at some of our formed clusters. And this is actually an interactive plot, so we can look around. So we can see here actually the clusters are quite close to each other, suggesting that these clusters are not too distinct. It's important to get an idea of the size of each of our clusters, and we can use the value counter method for that. And we see that our largest cluster is cluster 3 with 100 records, and our smallest is cluster 1 with 26 records. And now let's do some exploration into these clusters. So here I'm producing a pair grid for our numerical data, and I'm color coding it according to the records belonging cluster. And we can run this here, and we can see for each of our clusters the numerical statistics. As for our categorical data, I just produced some count plots as so. If we wanted to get more detailed cluster statistics, such as the mean or standard deviation, we can use the describe method and just filter our data to give us a given cluster. We can run this here. So we see here, for example, in cluster 0, we have a mean age of around 73, and we have a range from 60 to 95-year-olds. We see that the majority here is male, So here the encoding is 1 is male and 0 is female. We also have a mean serum sodium value of around 135. And we also see that the majority of people in this cluster do not smoke. So we can look at the cluster statistics for any cluster. So for example, cluster 2. And we can compare each of our formed clusters. So that's the end of this project, and I hope you guys learned something new. Thank you for watching.